Hello everyone, this is lesson 10, and today we're going to talk about 10 ways to destroy an Arduino board. In this lesson, we will teach you how to destroy an Arduino board. We will not use a sledgehammer, fire a bullet at it, or throw it into a pool. That's not what we're talking about here. We're going to show you how to electrically destroy your Arduino. Though many of you seem to already know how to do that through an unfortunate experience. Maybe part of your Arduino burst into flames, or there were sparks flying, or something like that. Or maybe a module just didn't work anymore. You know what we mean. The funny smell, the scorch mark on a component, or the program not in sync error message. These are all signs that you've just learned a lesson the hard way. Our goal is to avoid these 10 mistakes to increase the longevity of our board. Alright. So method 1 is shorting a I/O pin to the ground. So how do we accomplish this? First, configure an I/O pin to be an output, then set it to high. Short the pin to the ground. You have now created an overcurrent condition on the I/O pin, and it will be destroyed. Now why? So now I'm going to explain how this will destroy the board. So the why can get complicated for some of the methods. So you don't have to understand it completely, just know the theory behind how it basically works. Some of the stuff I'm going to say is high school level circuits or even higher. Alright, so this is a circuit inside the Arduino Uno board. So as you can see, these are the I/O pins. It goes through, enters through. This is inside the circuit, by the way, not outside. So 5 volts comes in, exits through the I/O pin, and then goes right to the ground. And then outside, we have connected a wire from here directly to the ground, so it becomes a full circuit, and there's basically no resistors besides the ones in the internal resistance, so it would short it because it has way too much current overflow. And if we look on our Uno board, then it can be any of these pins connected to the ground here, or any of these connected to the ground, or these can only be input, so these. So 0 to 13 digital pins, if they connect to the ground directly, then they will all be an overcurrent. Alright, so the microcontroller data sheet specifies an absolute maximum per pin current of 40 milliamps with a typical internal resistance of only 25 ohms per pin. A dead short to ground can allow as much as 200 milliamps of current to flow, more than enough to destroy the microcontroller pin. So the absolute max it can have is 40 milliamps, and with the internal resistance only at about 25 ohms, then the short will cause 200 milliamps, which is way more than the allotted 40 milliamps, sorry, and it will burn it up or maybe destroy something vital to our microcontroller. Alright, method 2 is shorting the I/O pin to each other. Shorting the I/O pin to each other. So how do we do this? We can configure two I/O pins to be outputs, then set one high and the other low. Now connect the pin together, and you have now created an overcurrent condition on both I/O pins, and they will be destroyed. Okay, so for this one, they can be any I/O pin if we set both of them to output. So it can be from 0 to 13. It can't be the analog pins because these can only be input, or they can output digital, but it's very rare. So if you connect one to the other, while one is set to low voltage and the other is high, then it'll short it. Alright, so why? The path of current flow is similar to method number 1 above, except the ground return path is through the microcontroller. So this would be even more devastating. And then I include a picture of the circuit inside the microcontroller. So, for example, number 6 is set to high, and then number 2 is set to low. Then the path will come through 6 and then back into the microcontroller through D2, and then it'll go to the ground, and then it creates a whole circuit which will go through all of this, and it'll be really bad for the microcontroller, probably damaging some parts. Alright, and then method number 3, apply overvoltage to the I/O pins. So how? We can apply a voltage exceeding 5.5 volts to any I/O pin. The I/O pin will be destroyed. So why? This diagram shows the flow of current when overvoltage is applied to an I/O pin. So this is what will happen. 5 volts comes in, and it goes through a diode, and then over here, more than 5 volts is put into our system, and that makes all the current go backwards and through here, and this I/O pin will be destroyed because the diode will be destroyed. And on here, it would be if you apply greater than 5 volts to any of these pins, then that pin itself will be destroyed. And any of these destructions will be really, really hard to repair. You would need specialized equipment, and even then it will become less compatible and everything. So once the voltage at the I/O pin is greater than the supply voltage of 5 volts by about excuse me, by about 0.5 volts, the top diode starts to conduct current. This is okay for diverting a short duration of over voltage, like electrostatic discharge. For example, if your hands touch the microcontroller when you have static, it's like in the winter when you touch something metallic and there's a zap. That is what's called electrostatic discharge. So that's okay if it's really a short duration, but if it's a constant overcharge of more than 5 voltage, then the diode will just be destroyed because it is not meant to be on all the time. It will simply burn out and stop protecting the pin. If the internal protection diode fails open, then the over voltage destroys the I/O pin. If the internal protection diode fails by shorting out, it's even worse, because now the overvoltage is applied to the entire 5-volt supply on the Arduino. So this is the protection diode I was talking about. If it goes through here for too long, then it will probably destroy it and burn it up, and then it could destroy the I/O pin or the entire 5 voltage supply on the Arduino. Alright, this means it will reach other components like the USB interface chip and destroy them too. So the USB interface chip is this here. This is the interface, but the chip itself is this one. It will destroy it, and then yeah, it'll be catastrophic. Did I forget to make? Yeah, I forgot to make this capital or bolded, sorry. And then method number 4 is apply external VIN power backwards. So many of you might not know what VIN is. I only went over this briefly. So VIN is this pin right here at the right corner of the power pins, and VIN you can enter in power just like through the power jack or the USB port. Alright, but it's a pin, so you can just use a wire. So how? You can power your Arduino through the VIN connector pin, but reverse the polarity of the VIN to ground power connection. You will destroy several devices on the Arduino. And why is this? That's because there is no reverse voltage protection on voltages applied to the VIN connector. Current will flow through the GND pin, ground pin, of the ATmega 328P. ATmega 328P is the main chip on our Arduino, which is this big one here. And then back up through the 5-volt pin and back through the 5-volt regulator and to VIN. And so the 5-volt regulator will be destroyed. So the 5-volt regulator is a module that allows voltages that are around 5 volts to be regulated and turned into 5 volts directly. But if it's a really big difference, then the regulator itself will be destroyed. So here's the circuit of inside the Arduino. This one is a little blurry, but as you can see, if the VIN is reconnected with reverse polarity, then it'll go through here and destroy the 5-volt regulator. And this is just an outline of everywhere it would go through and stuff it might destroy. Alright. Now method number 5. Numero 5. Apply a greater than 5 volt to the 5-volt connector pin. Oh, I forgot to make this a heading. Alright. And then how does this work? We apply a voltage of 6 volts or higher to the 5-volt connector. Many components on the Arduino will be destroyed. And this voltage can also appear on your computer's USB port. So not on the Arduino's USB port, but on the computer that you plug in your Arduino board onto can also be destroyed. So damaging your laptop or PC. And then how does this work? Possibly. Alright. So on the 5-volt pin, there is no protection on the 5-volt connector pin. This voltage is directly connected to the ATmega 328P microcontroller, and also the ATmega 16U2, which is the USB interface microcontroller. As well as the 5-volt regulator. So these three are all very important modules. The main chip, ATmega 328, and then the ATmega 16U2, which is the USB interface, and the 5-volt regulator that helps regulate voltage that are around 5 volts. And then all of which can be damaged by voltage exceeding 6 volts. And the resulting currents that flow. Here is an example current path through the ATmega 328P microcontroller. So over here, make it a little more smaller. Alright, so the 5 volts, it doesn't include, so this is the ATmega 328, and in this picture it doesn't include the USB interface or the 5-volt regulator. Alright, so disclaimer. It is a common misconception that the Arduino 5-volt regulator will ensure that the 5-volt voltage remains at 5 volts no matter what. It will not. Trust me on this. I learned the hard way. It will not. The only thing that 5-volt regulator can do is to control current coming from the USB port or the external DC power jack. If the current is coming from an external power source directly connected to the 5-volt connector pin, the regulator can do nothing about it. Another consequence of applying more than 5 volts to the 5-volt connector pin is possible damage to the PC's USB port. If the Arduino is powered from USB, then this excessive voltage can cause current to flow backwards through the voltage switching MOSFET T1 and back to the PC's USB port. Alright, so on here, if here we connect more than 5 volts, then it'll go back into the Atmel 328 and then go into the US Atmel 16U2, and then it might even go into the USB port and go through the USB and go out into our computer. And that would cause serious damage to the USB port on our computer as well. Alright, and then this is a picture of a more better picture of going through the power. If a greater than 5 volt is applied, it goes through here and goes into the USB VCC. The USB VCC is this one right here. Alright, and then method number 6 is to apply greater than 3.3 volts to the 3.3 volt connector pin. This is the same idea as the 5 volt connector pin. So how do we do this? We can apply a voltage of 3.3 volts or higher to the 3.3 voltage connector pin. Any 3.3 volt shields plugged in or other devices powered from this pin will be destroyed. If at least 9 volts is applied, this voltage can destroy the Arduino 3.3 volt regulator and also feed current back into the PC's USB port. Alright, so the 3.3 volt is right beside the 5 volt. It is this one right here. That 3.3 volt right here. Yes, alright. Why does this happen? Same thing as last time, the 3.3 volt connector pin also has no protection circuitry. How do you spell it? Circuitry. This voltage is directly connected to the Arduino 3.3 voltage regulator, and any other shields or devices that are powered by this connector pin. If the voltage exceeds 9 volts, the 3.3 voltage regulator, the 3.3 volt regulator. So this is basically the same thing as the 5 volt regulator, but instead of regulating current voltage to be 5 volts, it regulates the voltage to be 3.3 volts. This regulator will be destroyed and may allow current to flow backwards to the 5 volt node, and then backwards further to the PC's USB port. The excessive voltage will also destroy the two devices connected to the 5 volt node. The ATmega 328P and ATmega 16U2 microcontrollers, which are arguably the most important parts of the Uno board. So this is a picture. So if greater than 9 volts is applied over here, then it'll go here through the 3.3 volt regulator here and through here and into the USB, and it might possibly destroy a lot of things like the USB port, or as I said here, can go through the 5 volt node and go into the ATmega 328P and the ATmega 16U2. Alright, so that's method 6. After that is we short the VIN to the ground. So how do we do this? We can power the Arduino from the DC power jack, and we short the VIN connector pin to the ground. The Arduino blocking diode will be destroyed, and traces on the Arduino PCB may melt and be destroyed. Alright, so connect through the VIN, and then it's short from VIN to the ground, which is ground is over here. It can short the circuit from the DC power jack input, and it can destroy, and when it says PCB, it means the board itself. The board itself is PCB, and then it can destroy some of the traces on it. And the blocking diode, of course. Alright. And why does this happen? So there is no current limit protection on the VIN connector pin. I think we talked about this earlier. A short circuit from the VIN to the ground effectively shorts the circuit from the DC power jack input and exceeds the current rating of the blocking diode. So here's a diagram of the circuitry like this. So this is the DC power jack, has 1, 2, 3 inputs. So 1 or 2 is input like this, goes through here, and goes through the VIN this way, and then if it's here to the ground, then the VIN is shorted, and then this can destroy the things we mentioned above. Alright. The amount of current that flows is limited only by the resistance of the Arduino PCB traces and the current capability of the power supply. If this is high enough, the diode, why is diode capitalized? Sorry, diode D1 will be destroyed and PCB traces may melt due to the heat caused by this large current. Alright, so this is method 7. It's quite disastrous. Now onto method number 8, which is we apply 5-volt external power with a VIN load. So this is one of the most common mistakes that people make, and most people know that it's a mistake, but they do it anyways because they might be lazy, or they might, on some boards I'm pretty sure you might be able to do it. Don't quote me on that though, I'm not too sure. So if you are powering the board from 5-volt applied to the 5-volt connector pin, and your circuitry connected to the VIN pin, or have shorted VIN to ground, then current will flow backwards through the 5-volt regulator and destroy it. So again, the VIN pin is this pin right here to the most right of all of the power pins. Alright, so if there's a load on here between the ground, then let's explain how this could cause disaster. So there is no reverse voltage. There's no reverse voltage protection. There is no reverse voltage protection on the 5-volt regulator, thus current can flow from the 5-volt connector pin backwards through the regulator pin, or through the regulator, and to whatever is connected to VIN. So in this case, the load is typically a motor. Motors should be added to the circuit with an independent battery. Alright, so here's a example of the circuit. Alright, so this is the load in between the 5-volt and the ground, but since the 5-volt external is to the VIN load, so it goes this way now and to the ground, and that is bad, very bad. Alright, so next, method number 9 is to apply greater than 13 volts to the reset pin. Alright, so the reset pin is in the power. It's the third one from the left. This one right here, it's RES, which stands for reset. And yeah, it's kind of like the reset button, but you need to apply voltage through it. Alright, so how does it work? It applies greater than 13 volts to the reset connector pin. Oh man, my typing is all over the place today. And then if we apply greater than 13 volts to the reset connector pin, the AT-MEGA328P microcontroller will be damaged. Microcontroller will be damaged. And why is this? The reset connector pin is directly connected to the reset pin on the ATmega328P. And while this pin tolerates up to 13 volts, higher voltages will damage the device. So in this diagram, so if 13 volts or higher is applied through here, and then the reset pin goes into the reset through the reset pin into the ATmega328 and frying everything within it, and goes into the ground and completes the circuit. So this will destroy the ATmega328P. This is not really common, but it can happen, so be aware of it. And then method number 10 is exceed total microcontroller current. So when you're making complicated projects, this becomes very, very important. Don't forget this. So how? So total microcontroller current is for any of these pins, analog input, and all of these digital pins. Okay, so configure at least 10 I/O pins to be high and draw 20 milliamps from each one. So this in itself can cause a problem. For example, an example of using 10 I/O pins is by lighting 10 LEDs. You have now exceeded the total supply current rating for the microcontroller, and it will be damaged. So why does this happen? It's not enough to limit the current of each I/O pin. The total current sourced from all I/O pins must not exceed 200 milliamps. By the way, this is according to the ATmega328P datasheet. So if each one draws 20 milliamps, then it'll go multiply that by 10 and it'll be 200 milliamps. And if it's more than that, then it cannot be sourced more than that. So the microcontroller will probably be damaged. So here's a diagram. So 18 mega power, then this is the thing, 5 volts. Alright, yeah, self-explanatory. And then now that we talked about 10 methods for destroying it, let's talk about some safety regulations to stop these methods from happening. Because destroying a board would not be fun. You have to rebuy it, and it costs money, and it might give you a good scare. So safety regulations. Alright, so number 1, plug and unplug modules and jumpers without power. So what this means is that in here, if you're going to start connecting pins onto a breadboard or something, then make sure this is not connected onto your USB. Make sure you unplug it whenever you need to change your circuit for your breadboard or something like that. Okay, and then steps to modify the circuit. Unplug the USB cable, modify the circuit, check and reconnect the USB cable. Alright, so this is basically the same as last step. And then be sure to check the circuit connection before powering on. So before you plug it in, you need to make sure that all the connections are working, you're not shorting anything, and yeah, make sure it doesn't coincide with any of the 10 methods. Alright, number 4, necessary experimental protection, such as safety glasses, because some of the modules, for example, a resistor or something like a capacitor, they might explode and cause sparks or maybe some flames if it's a lot over, something like that. So safety glasses, or maybe some gloves, experimental protection equipment. Alright, and then if there is severe heating, smoke, fire, or abnormal noise during the experiment, unplug the USB cable immediately and cut off the power. Alright, so severe heating doesn't mean like your phone is overheating. That's not severe heating. Severe heating is like something is becoming red or something. And then smoke, self-explanatory. Fire, there's like light being produced. And then abnormal noises, things that aren't normally supposed to happen. When this happens, you need to unplug the USB immediately so that the damage won't go through to your computer, and cut off the power so that it can't inflict more damage on any of the other modules in your Uno board or your modules that you included into your circuits. And lastly, before the experiment, self-assess the experimental risks. The experimenter shall bear the personal or property losses that may be caused by the experiment, as well as the foreseeable or unforeseeable risks. So I stole this line from the disclaimer, but it is quite important. The experimental risks are not from the factories or whatever produces your Uno board or your components. The risks are your own, and you must take responsibility for the personal or property losses. Alright, so before you plug in your circuit and try if it works, make sure that it won't damage anything permanently. And yeah, that's about it for this class. Thank you for watching, and see you next class.